Let's continue talking about the reduction of alkynes. So here, just a reminder of the three different ways you can reduce alkynes. And you can use hydrogen or a metal catalyst, like a palladium and carbon. And that is the same catalyst that we were using for reduction of alkenes. And the result is that you will get the complete reduction. So the alkyne, the triple bond, will go to a single bond, just one sigma bond. So you will have a reduction all the way from the alkyne all the way to the alkane. Results are rather interesting here. If you have the 2,2-dimethyl-3 nonine and you reduce that, what do you get? You will get a 9 carbon atom, 2, 3, 4, 5, 6, 7, 8, 9 carbon atom compound with a couple of methyl groups in the second carbon atom, right? If you were reducing the 8,8-dimethyl-3 nonine, the result will be that you will get 2, 3, 4, 5, 6, 7, 8, 9 with a couple of methyl groups in the second carbon from the other tip. So actually, these two compounds are the same, right? That is an interesting thing, that a reduction of two different alkynes yield the same alkane final product. And then we had the two methods of partial reduction. We can say partial reduction because we are going from an alkyne to an alkene. And this is interesting. Even if you have excess of hydrogen, the reaction will not proceed any farther than the alkene, and the reaction will stay there in the alkene. And the stereochemistry of the reaction is very well defined. It proceeds with syn stereochemistry. That means that the delivery of the two hydrogen atoms take place from the same side of the molecule. And that's why you get the cis alkene. If you really, really want to get the alkane, in that case, you will have to use hydrogen and palladium in order to go from the alkene to the alkane. Then we have the other method of reduction is using lithium in ammonia. I told you, you can also use sodium in ammonia. Sodium in ammonia works equally well. And the result here, unlike the previous case where you get the cis alkene, here you get the trans. So that is great because that is giving us a very, very good flexibility in the all different kinds of compounds that we may want to prepare. So, and here we have the mechanism for the reduction with lithium in ammonia. A pair of electrons of the alkyne will react with lithium. That means lithium is providing one electron. Lithium is providing one electron to the carbon atom here. And then ammonia is providing one proton, right? And then you go through a second round that another lithium will give you one additional electron to become lithium plus. And then the new anion that you have just formed will react again with another molecule of ammonia. And in that way, you get the final product that is the transalkene. And here we go now with the very beginning of the very, very important formation of the acetylide anion. and the subsequent alkylation. So why is this so important? Well, because you see, sodium amide, the conjugate acid of amide, of NH2 minus, is ammonia. And the pKa value of ammonia is around 35, 36. So because of that, this is going to be basic enough to abstract a proton, and then you can end up with a lone pair of electrons on the sp hybridized carbon atom. And then that carbon ion, we can utilize that carbon ion in two different ways. It can react as a nucleophile. What does it mean, a nucleophile? A nucleophile means that it will be looking for some other carbons with a low electron density, and it will get attached to that carbon atom. The other possibility is that it can act as a base. When it acts as a base, well, it will be looking for protons. It will abstract a proton from another species, and then it will get protonated. The acetylide anion will get protonated. So this is the first example that we have. You have step number one, reaction with sodium amide. So the sodium amide, the NH2 double dot minus, that is going to abstract the proton, and the pair of electrons will stay on the sp hybridized carbon atom. And then step number two, we have reaction with butyl bromide. So where is the delta plus and delta minus in my butyl bromide? So I will have a delta minus on the bromine and a delta plus on the carbon. So the CH3, CH2, 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 1, 2, 3, triple bond C double dot minus. This is going to attack that carbon atom there, and it will displace the bromine. And that's how you get formation of a 10 carbon atom product, and you get formation of 5 design. Okay, I will stop here, and I will continue a little later.